Welcome back to our series on introductory statistics. I'm Mark Ledbetter. This is lecture video 27, part C. We are in section 8.1. This is the third and final part of that section. So we've been talking about how to calculate a confidence interval for mu, the population mean, when we know sigma, the population standard deviation. And last time we did an example, and in addition to the calculations, we added the interpretation. So this is the standard sentence or model that you want to use to interpret a confidence interval. Okay? So what we're going to talk about now is something that you do before you do a study. You need to determine the sample size in order for you to get good results. So we want a confidence level C, that we're going to determine that before we do the study. And the confidence level is usually at least 90% or at least 0.9. Okay? The default is 0.95. That's just seems to be universally accepted, but you should be conscious and careful about choosing that level of confidence that you need for the study. The bigger the confidence level and the smaller the value of E, the larger your sample size will need to be. So we have to be very careful about choosing these values. So we want a certain confidence level that we're going to set and say we want to be this confident in our results. And we need to determine what value of error, which determines the width of the confidence interval. We need to determine just how much variation or error or length we can have to the confidence interval. And we're going to set that amount. And we're going to say that this is the maximum amount of error that we can tolerate in the results. Okay, so we do not want to exceed this value of E. We want to have a good enough precision to the confidence interval. Okay, so how do we do this? Well, the book talks about the requirements for calculating the sample size, and they say that the distribution of X bar needs to be approximately normal, or in order for X bar to be approximately normal, if we don't know the distribution of X, we know that we need an N of at least 30. So as long as our result here for sample size is 30 or higher, then we're okay. But if our result comes out less than 30, then we would need to go back to the original distribution and make sure that it has a normal distribution, or our results may not be meaningful. Okay? So what we've done is we've taken the formula for E, which is Z sub C sigma over the square root of N, and we've solved for N. So we multiply by the square root of N on both sides, and so this cancels. And then we have square root of N times E equals Z sub C Z sub C sigma. And we want to isolate N, so we divide both sides by E. And so the E cancels out on this side. And then we need to square both sides so that we get N instead of N of the square root of N. So this gives us N is equal to Z sub C sigma over E quantity squared. Please don't forget to square the value. That's a common mistake students make. Okay, so once we calculate N, we have this rule that's very important. If N is not a whole number, then we increase N to the next higher whole number. It doesn't matter what the decimal place is, we're going to take N and up to the next whole number, no matter what. And this keeps us from having an error, a value of E that's actually larger than what we want when we calculate our confidence interval. Okay? So the result is the minimum value of n needed to have a value of e that's not larger than the amount that we specify or desire. And often we don't know the value of sigma. Okay? So if we have a preliminary study of at least n equal to 30, or a study with n greater than or equal to 30, then we can use the value of S, the sample standard deviation, in place of sigma. But that's only for this formula, not for anything else. Okay? All right. So let's do an example. A researcher wants to determine the average or mean weight of salmon caught by a certain fishing company up in Alaska. A preliminary study of n equals 50 had a standard deviation of S equals 2.15 pounds. How large does our sample size need to be in order to have a 99% confidence level, and to be 99% confident that the sample mean, which is x bar, is within 0.2 pounds of the true mean weight mu? Okay, so let's look at our requirements. So n is equal to 50 in preliminary study. Greater than or equal to 30, yes, so use 2.15 for sigma in the formula, okay? Is n greater than or equal to 30? We don't know that yet. So we're not told whether this distribution is normally distributed or not, so we need to do the calculations before we know if we're okay here. What's C? Well, here's 99% in front of the word confident. So C is going to be 99%. We go to our table to find Z sub C. And for 99%, we see that Z sub C is 2.58. Okay, so 2.58 is our value of Z sub C. Now, we need E. Remember that the definition of the margin of error was the absolute value of x bar minus mu. And in the problem, we say that the sample mean is within 0.2 of the true mean mu. So they're saying that this is equal to 0.2. So this is 0.20. Okay? So now that we have all of these values, we can plug into the formula for n. So Z sub C is 2.58. And we have sigma is 2.15, and then E is 0.20. And we're going to get a value, don't forget to square it. So 2.58 times 2.15 divided by 0.2 equals 27.735. But remember, you need to square this. So we square this and we get 769.23, etc. This is not a whole number. We have a decimal. It doesn't matter what the decimal is. We're going to increase this to the next higher whole number, which is 770. So that's our answer. We need at least 770. This is greater than or equal to 30, so we're okay as far as our requirements now. Yes. N equals 770 is going to be required. So we'll know that at that level, X bar has approximately a normal distribution. Kind of a backwards way of doing things, but that's how our book does it, so that's how I'll teach it for this class. Okay, so that I'm consistent with them. All right, I want to point out something that, remember that the confidence interval is given by x bar minus e to x bar plus e, and the e is equal to z sub c times sigma over the square root of n. And so if c is bigger, z sub c is bigger. Let's see that in our table. So here's c. As c gets bigger, z sub c gets bigger. Likewise, as c gets smaller, z sub c gets smaller. Okay? If c is smaller, z sub c is smaller. So e here would be bigger. E here would be smaller. Okay? So what happens as we increase n? As n gets bigger, square root of n gets bigger, and e gets smaller, because square root of n is on the bottom. So if we divide by a bigger number, we get a smaller number. As n gets smaller, square root of n gets smaller, e gets bigger. So, increasing the confidence level and keeping everything else the same will make our confidence interval bigger. Decreasing C, which is not always a good thing, having a lower level of confidence is not desirable in most cases, but decreasing that gives us a smaller interval. We want a smaller interval. It's better. So normally what we'll do is we will increase n, and that will give us a smaller value of e. Okay? So increasing the sample size reduces or decreases the size of our confidence interval. It's important to know that relationship. Okay, so that's it for this video and this section. Please make sure you update your formula sheet. If you have questions, come to virtual or physical office hours. If you need help before that time, by all means, email me. I'm always happy to help with the course content. Please take care of yourself, stay safe, because we want to see you here next time.